Alright, so where did we stop in the morning? We stopped at a place where we talked about the multi-valued nature of the argument function, right. So now here are the list of exercises for you. So this is an exercise, some of these are probably familiar to you. Cos theta plus I times sin theta to the power n is cos n theta plus I times sin n theta for all n. Determine the fifth roots of unity in terms of radicals. You have probably computed the cube roots of unity. Now take up the fifth roots of unity and then you take up the seventh roots cos 2 pi by 7 plus I times sin 2 pi by 7. Show that omega satisfies a cubic equation with integer coefficients. Determine the fifth roots of unity in terms of radicals. It's not enough for you to tell me that cos 2 pi by 5 plus I times sin 2 pi by 5. No, that won't do. You have to write it in terms of radicals. And then you take the seventh roots of unity, show that it satisfies a cubic equation with integer coefficients. You can even write down the 17th roots of unity in terms of radicals, quadratic radicals. That was discovered by Gauss. There is a correction. So let me just point out this correction. Slide number 24. Problem number 3. Show that W plus 1 over W. This is the correction. So show that W plus 1 over W satisfies a cubic equation with integer coefficients. Find this cubic. Right. W plus 1 over W, right. Is this clear? Please make this correction, incorporate this. So W plus 1 over W is 2 cos 2 pi by 7. 2 cos 2 pi by 7 satisfies a cubic equation with integer coefficients and find this cubic. Is that okay? Prove that sin to the power 4x is 1/8 of cos 4x minus 4 cos 2x plus 3. And the fifth problem is z1, z2, z3 are three distinct complex numbers. They form an equilateral triangle if and only if z1 square plus z2 square plus z3 square is z1 z2 plus z2 z3 plus z3 z1. Right. Then there are some problems on sketching some loci, some pictures. You have to draw some pictures in the plane, point out what these curves are or what these regions are or what these sets are, depict these sets in the plane, sketch the loci, right. So what is item number 1? Z such that mod of 1 plus z upon 1 minus z is 1. What is it? What is this? What is this supposed to be? It's the, what is this geometrically, what is this? No, it's a straight line. It is a perpendicular bisector, right? I mean, the distance of z from 1 is the same as the distance of z from minus 1. The perpendicular bisector of the line segment joining 1 and minus 1. Correct. And what about the third one is an ellipse? The third one is an ellipse. Second one is a circle. That's correct. All right. Is it clear? Written down. The fifth question is a very popular problem. If you look at the people studying for joint entrance examinations for IIT, Everybody will know that, all the JEE students. But then when I present them the solution, they are a little surprised because the kind of solution that I present is very different from what they have ever imagined. We will discuss this. There is an elegant way to do this problem. Right. Next, shall we proceed further? Some more exercises here. Suppose if mod z equal to 1, show that the complex number z minus a upon 1 minus a bar z has unit modulus, where we are not explicitly spelt out what the bar means. Here it is, the definition. If w is x plus iy, w bar is x minus iy, it's called the complex conjugate of w. The complex conjugate has some very simple properties and they form the content of exercise number 8, and you are familiar with exercise number 8. There isn't much to be done there. It is just there for completeness, the basic properties of the modulus. What are the basic properties of modulus? The sum and the product are both real, right? W plus W bar is a real number and W bar is also a real number, correct? W plus W bar is twice the real part, correct? Yeah. Those are very easy properties of the complex conjugate. All right. Here are two more problems. Show that the images of concentric circles centered at the origin under the map fz equal to z plus 1 over z constitutes a family of confocal ellipses. What about the images of rays emanating from the origin? One of these circles, one of these ellipses will degenerate. I'll leave it to you to find out which one of them is. You're looking at images of concentric circles, right? R x equal to r cosine t, y equal to r sine t. So the complex number z is r into cosine t plus I sine t, correct? And then you're looking at f of z equal to z plus 1 over z. So write f of z as u plus IV. So you will get u in terms of r and t, v in terms of r and t. R is fixed because a circle, right? R is fixed. So t is a variable along the curve. So you have to eliminate t. You obtain, you put in z equal to r cosine t plus IR sine t. Then you write f equal to u plus IV. So obtain u in terms of r and t, v in terms of r and t. Eliminate t. You will get an equation connecting u and v, that is the image of the circle. Correct? So find out what those images are. Show that it forms a family of confocal ellipses. Likewise, I am asking you for the images of rays emanating from the origin. Next question is similar. Show that the image of the horizontal line mz equal to c under the map fz equal to z squared is a parabola with focus at the origin. Interesting exercises you can assign for your students, right? Is that okay? Probably these exercises are less familiar to you. Some of these exercises are probably new. Cos theta plus I times sin theta to the power n is cos n theta plus I times sin n theta. There is a familiar exercise. These are probably not so familiar. but it's worthwhile doing them. Right? All right. Now that we continue with the theory. Now, the field of real numbers, I said in the morning, is a ordered field. There is a ordering relationship. There is an order relationship, right? X less than y. When is x less than y? When y minus x is a positive real number. Correct? So, if x is less than y and c is a positive number, then cx will be less than cy. If x is less than y, then x plus c is less than y plus c. So, there are these properties that the order relation in some sense interacts with the addition and multiplication of real numbers, right. So, now how do you formalize this concept? How do you define an order relation on the real numbers? The way to do it would be to identify a certain subset of the real numbers called the positive reals. This subset should be non-empty, of course. It should not contain 0, correct? And if the order relation should interact with the field properties, that is the field operation, the addition and multiplication, that means that this subset of positive things should be closed under addition and multiplication, right. Sum of two positive things should be positive and product of two positive things should be positive, correct. There is one more property that you want this thing to have. Given any real number, either that real number should be in this distinguished set, or minus of that should be in the set, or that thing is 0. Given any real number x, either x is 0 or x is in S or minus x is in S, where S is the set of positive real numbers. So, the whole concept, and then once you identify this subset of positive reals, then we say that x is less than y if y minus x is positive, correct. So, to define to establishing an order relation on a field means is the same as identifying this particular subset. So, let me formalize the whole thing. So, recall that the field of real numbers is an ordered field. Do not have to write all these things because it will be put up in the Moodle, and some of these things are quite familiar. In fact, most of it is quite familiar to you, but this is a revision. That is, to say it is an ordered field means there is a non-empty subset S of R such that 0 does not belong to S, number 1. If you take two elements from S, the sum and the product should both be in S. Third is the law of trichotomy. Given any x in R, either x is in S or minus x is in S or x is 0. Now, once you have this particular thing in place, you could say that given x and y in R, we declare x is less than y if y minus x is in S. Then one proves the usual properties of the relationship, namely if x is less than y, then x plus c is less than y plus c, and so on. The usual properties of the order relation can be proved. However, for the complex numbers C, the situation is different. Such an ordering is, for the complex numbers, such an ordering is impossible. You cannot have an ordering in the field of complex numbers which interacts with addition and multiplication. So, this is stated in the form of a theorem. It is impossible to find a non-empty subset of C such that 0 does not belong to S, Z1 Z2 belong to S implies Z1 plus Z2 belongs to S and Z1 Z2 belongs to S. Third, given any Z in C, precisely one of the following holds, either Z is 0 or Z is in S or minus Z is in S. It is not possible to find such a non-empty subset of C. Right. So, it is not possible to establish a order relation in the field of complex numbers. The field of complex numbers cannot be made into an ordered field. So, in this respect, the field of complex numbers differs from the field of real numbers. Right. Let us prove this. Suppose such a set S exists. Suppose such a set exists, we will arrive at a contradiction. Well, I is not 0, so either I must be in S or minus I is in S. Now let us take the case 1 when I is in S. Well, if I is in S, then I into I must be in S, so minus 1 is in S. But then I is in S and minus 1 is in S, so the product is in S, so minus I is in S. So both I and minus I are in S, which is again a contradiction. It contradicts the law of trichotomy. So that leads to a contradiction. Case 2, minus I is in S, that is also going to lead to a contradiction, same contradiction. Minus I is in S, so minus I into minus I is in S, so minus 1 is in S, but I is minus I into minus 1, that is again in S. So both I and minus I lie in S, so it is a contradiction. So you cannot order the field of complex numbers. Argument is clear? Okay. Good. The next thing under this chapter is the existence of nth roots of a complex number. Existence of nth roots of complex numbers is the next item, and the fundamental theorem of algebra. So the theorem is every non-zero complex number has precisely n distinct nth roots. Every non-zero complex number has precisely n distinct nth roots. So let us take z not equal to 0, and let us call the principal argument of z as theta. Let theta denote the principal argument of z, and let us consider the complex numbers cos theta by n plus I times sin theta by n, cos theta by n plus 2 pi by n plus I times theta by n plus 2 pi by n, and so it goes, cos theta by n plus 2 pi k by n plus I sin theta by n plus 2 pi k by n, where k runs from 0 to n minus 1. These are n distinct complex numbers. Is an exercise for you to check that these are distinct. The argument is very similar to what we have done. Remember earlier we did cos of theta prime equal to cos of theta double prime. Sin of theta prime equal to sin of theta double prime means that mod of theta prime minus theta double prime is 2 pi k, etc. The similar argument has to be used. So prove that these complex numbers are all distinct. Right? Prove that these complex numbers are all distinct. It's not difficult to do it. Right? Alright, then what do we do once you know that these are distinct? Then let us take these things. You take your z to the power 1 over n, mod z, right? Mod z is non-zero. Mod z is a positive real number. Z is not 0. So mod z is a positive real number, and a positive real number has a nth root, which a unique real positive nth root. Why is that? How do you prove that? Every positive real number has a unique positive nth root. How does that come from? Where does that come from? Yeah? What? Fundamental theorem of algebra has not been established yet. Archimedean property, yes, but then considerable amount of work has to be done. It's not simply a direct consequence of the Archimedean property. What is the Archimedean property? Given any real number x, there is a natural number bigger than x. Let us look at the field of rationals. Does it satisfy the Archimedean property? Given any rational number x, there is a natural number bigger than x. The rationals also satisfy the Archimedean property. So just the Archimedean property will not give you. You need more than the Archimedean property. Archimedean property is one of the components which is required in the proof. That I will agree with you. I will agree with you that Archimedean properties is one of the things that will go into the proof. There are several proofs, by the way. So I don't know which proof you are thinking of, but whichever proof maybe the proof that you are thinking of uses the Archimedean property, but just the Archimedean property alone will not suffice. You have to do more work. Exactly, you need the completeness. Absolutely correct. Archimedean property and completeness are both required to prove this. Well, the simple argument would be the following. Look at the function f of x equal to x to the power n. Is it a continuous function? It is a polynomial, so it is continuous. What is f of 0? 0. What happens to f of x as x tends to infinity? It tends to infinity. What does the intermediate value theorem tell you? The intermediate value theorem tells you that it should take all values, right, between f of 0 and f of a, and you allow a to become larger and larger. F of a becomes larger and larger. In other words, the function f of x equal to x to the power n takes on all positive real values as well as 0. So pick any number b, there must be an x such that f of x equal to b. In other words, pick any positive real number b, there is an x such that x to the power n equal to b. Correct? So every positive real number has a nth root, and nth root is also unique. The real positive nth root is unique. Are we really using the Archimedean property and the completeness property in this proof that I just given you? Yeah. Where is the Archimedean property and the completeness property being used in this argument? The intermediate value theorem is a non-trivial theorem. The intermediate value property of continuous functions is non-trivial, and in order to prove it, the completeness of real numbers is very essential. The completeness of real numbers is very essential in order to prove this. Right? All right. So let us get back over here. Now define, now mod z is a positive real number and its unique positive nth root is mod z to the power 1 over n. And then I am putting this stuff cos of theta by n plus 2 pi k by n plus I times sin theta by n plus 2 pi k by n, where k runs from 0 to n minus 1. So now I had now written down k distinct complex numbers, right? N distinct complex numbers. I written down n distinct complex numbers. Let us raise them to the power n. What do you get? Mod z into cos theta plus I times sin theta, which is z. So now we have given a z not equal to 0, we have displayed n distinct nth roots. How do you know that these are the only ones? How do you know that there are no more than n? That is the next thing. Now we show that it cannot have more than n roots. Let us proceed with the proof that there are no more than n roots. Suppose, I will take your question later. Suppose that there is a w such that w to the power n is z. Since z is not 0, w cannot be 0. So let phi be its principal argument. then W is mod W cos phi plus I times sin phi. Now what are the equations that W to the power n equal to Z give you? It will give you mod W to the power n equal to mod Z or W equal to mod Z to the power 1 over n. Remember, we are talking about we are talking about the positive real nth root, and that's unique. So now in this equation, you put all these things in this equation, and what are you going to get? You are going to get this equation, right? Cos phi plus I times sin phi to the power n equal to cos theta plus I times sin theta. This equation. Mod W to the power n will be mod Z. That will cancel out from both sides. You are just going to be left with this. Theta is also in the, I have taken theta to be the principal argument of Z, and phi is the principal argument of W. Okay. So now use the exercise. What is this? Cos n phi plus I sin n phi. So we get this pair of equations, cos n phi equal to cos theta, sin n phi equal to sin theta. That means that n phi minus theta is 2 pi k, where k is an integer, or phi equal to theta by n plus 2 pi k by n. Correct? Alright, so far clear? Alright. So now let us continue. But where is this phi? Phi is in minus pi to pi. Where is theta? Theta is also between minus pi and pi. If theta is between minus pi and pi, theta by n is also between minus pi and pi. Correct? So the difference phi minus theta by n is strictly less than 2 pi, right? But what is this phi minus theta by n absolute value? In the previous equation is here. It is 2 pi mod k by n. 2 pi cancels out, you get what? Mod k is strictly less than n, or mod k is less than or equal to n minus 1. So what are the choices now? K equal to 0, 1, 2, 3 up to n minus 1, or k equal to minus 1, minus 2 up to minus n minus 1. So let us assume that k is less than 0. If k is less than 0, then I can surely write, if k is less than 0, I can write cos 2 pi k by n plus theta by n as cos of theta by n plus 2 pi k by n plus 2 pi. Then what happens to this? These two things over here, that becomes k plus n by n. Correct? 2 pi into k plus n by n. Right? Then all right. So let us do that. So now I can write down cos theta by n plus 2 pi k by n plus I times sin theta by n plus 2 pi k by n, same as add the 2 pi to both the angles and you get it in this form. Correct? You get it in this form. What do you know now? Remember, k was negative, isn't it? K was negative and mod k is less than or equal to n minus 1. So you have this inequality, minus n plus 1 less than or equal to k less than 0, which means that 1 less than or equal to n plus k less than n, right? That's what you have here. So this number is the same as this number for a different choice, but this choice, this new choice, this new k is in the range from 0 to n minus 1. So we get nothing new. So it is enough to let k run from 0 to n minus 1, and because the negative values of k are just going to give you the same values again. Correct? Is that correct? So there are exactly n distinct nth roots of every non-zero complex number. So this theorem is a very special case of the fundamental theorem of algebra. What is the fundamental theorem of algebra? Every non-constant polynomial with complex coefficients has a root, has a complex root. We have to wait for some time before we can prove the fundamental theorem of algebra. We shall prove the fundamental theorem of algebra later. Right. So, this is the completion of the first chapter. So, with this, the first chapter is closed. We have, let us recapitulate what we have done. We have introduced the complex numbers, we have introduced addition and multiplication of complex numbers. We have verified that with this addition and multiplication, the complex numbers forms a field. It has the real numbers as a subfield, right? And this particular field cannot be ordered, right? And we have discussed, and every non-zero complex number has n distinct nth roots, right? And we have the fundamental theorem of algebra that every non-zero, every non-constant polynomial has a complex root, and we have discussed arguments, principal arguments, the argument function, and the multivalued nature of the argument, and so forth. So, although much of this will be repetition for you, I suppose we are looking at it at a slightly advanced, looking at it from a slightly advanced standpoint. It is not the way it is being presented in elementary textbooks, right? Elementary textbooks don't talk about fields and ordered fields and the multivalued nature of the argument and careful discussion of, nth roots and all. That's not available in all elementary books, and so since the course is for college teachers, the course will proceed at a slightly higher level rather than what I would teach in my BTech courses, because that's for students who have not seen the material before. All right. So, this I conclude the first chapter, and we shall now take up the problem sheets. Okay, thank you.